Take a sip of ocean water and you'll immediately regret it. It's intensely salty. Now drink from a river, and it tastes completely normal. Just plain water. Here's a genuinely surprising fact. Rivers actually contain salt too. Wait, what? If rivers have salt, why don't they taste salty at all? And if rivers are constantly flowing into the ocean, why doesn't the ocean just stay fresh too? The real answer is a slow, genuinely fascinating process that's been running for billions of years. And it involves a mistake scientists once made trying to use this very process to calculate Earth's age. Let's get into it. Let's start with that surprising fact. Rivers genuinely do carry dissolved salt and minerals. It happens through a process called weathering. Rain absorbs a small amount of carbon dioxide as it falls. That makes rainwater slightly acidic, just enough to slowly dissolve minerals out of rock. Those dissolved minerals, including sodium and other salts, get carried along by streams and rivers. The amount is small, roughly 200 times less concentrated than ocean water. That's exactly why it doesn't register as salty to your taste buds at all. This weathering process has been running continuously since Earth's very first rains, billions of years ago. Every mountain range, every rocky riverbed, has been slowly contributing tiny amounts of mineral runoff. Multiply that by millions of rivers, over billions of years, and the totals become genuinely enormous. So if rivers are constantly picking up new salt, why don't they just keep getting saltier over time? The key is that rivers are constantly moving. They're a passageway, not a final destination. Whatever salt enters a river gets carried straight through and delivered onward to the ocean. Nothing sits still long enough in a flowing river to build up to a noticeable concentration. The ocean is a completely different situation. It's essentially the final stop for all that water. Here's the crucial part of the puzzle. Water constantly evaporates from the ocean's surface. When water evaporates, only pure water molecules lift into the air. The dissolved salt stays behind. That evaporated water eventually falls as rain, feeding rivers, which pick up brand new minerals from rock. Those rivers then carry that new salt straight back into the ocean, joining what's already there. The water keeps cycling in a loop. The salt mostly doesn't. It just keeps quietly accumulating. Over hundreds of millions of years, that slow, one-directional accumulation adds up to a lot of salt. Rivers aren't even the only source. There's another surprising contributor deep underwater. Along certain parts of the ocean floor, hydrothermal vents release mineral-rich hot water directly into the sea. These vents form where seawater seeps down through cracks near volcanic activity, gets heated, and shoots back out. Along the way, that heated water picks up even more dissolved minerals from the surrounding rock. It's a completely separate, ongoing source of ocean salt that has nothing to do with rivers at all. There's actually a perfect natural experiment that proves this whole explanation. It's called a terminal lake. A terminal lake is one that has rivers flowing in, but no river flowing back out. The Great Salt Lake in Utah and the Dead Sea are two famous, real-world examples. Water still evaporates from these lakes just like the ocean does, leaving salt behind every single time. But since there's no outgoing river to flush anything away, the salt has nowhere else to go. Over time, that trapped salt becomes extremely concentrated, sometimes even saltier than the ocean itself. The Dead Sea, for example, is roughly 10 times saltier than typical ocean water. It's essentially the ocean's exact same process, just sped up and trapped in a smaller, closed basin. Now here's that historical mistake I mentioned earlier, and it's a genuinely great science story. In the late 1800s, some scientists had an idea. If they knew how fast rivers deliver salt to the ocean, they could calculate how long it must have taken to make the ocean as salty as it is today. That number, they figured, would reveal roughly how old the Earth itself must be. Their estimates came out to only around 100 million years old. Far too young, as it turns out. The method had a major flaw. It assumed salt only ever goes into the ocean and never comes back out. We now know that isn't true. Salt also gets removed from the ocean through other natural processes. So what actually removes salt from the ocean over time? A few genuinely interesting processes. Marine organisms like corals and certain plankton use dissolved minerals to build their shells and skeletons. When those organisms die, their mineral-rich remains settle and become part of the ocean floor permanently. Salt also gets trapped when parts of the ocean become cut off and evaporate completely over time. This creates massive underground salt beds, some discovered miles beneath the modern ocean floor. Because of these removal processes, ocean salinity has actually stayed roughly stable for hundreds of millions of years. It's not an endless one-way buildup. It's closer to a slow, balanced equilibrium. So if the salt method was flawed, how did scientists eventually get Earth's real age right? The breakthrough came from an entirely different area of science: radioactive decay. Certain elements decay into other elements at an extremely steady, measurable, predictable rate. By measuring that decay inside ancient rocks, scientists could calculate age far more reliably than salt ever could. This method eventually revealed Earth's real age, approximately 4.5 billion years old. That's roughly 45 times older than those original 19th century salt-based estimates. It's a great reminder that even a flawed early theory can still point science in a useful direction. This whole system also explains why ocean saltiness isn't exactly the same everywhere on Earth. The Red Sea is noticeably saltier than average because it sits in a hot, dry region with heavy evaporation. The Baltic Sea, by contrast, is much less salty, thanks to heavy rainfall and many rivers flowing into it. More evaporation without much fresh water coming in means higher salt concentration in that specific region. It's the exact same global process, just playing out differently depending on local climate and geography. Quick pause before we continue. Take a guess. Do you think all the salt in the ocean could theoretically be removed and harvested? In a technical sense, yes, and people already do this on a small scale through salt evaporation ponds. But the ocean holds an almost unimaginable amount of dissolved salt, far beyond anything humans could fully extract. Let's clear up a few common myths before we wrap up. Myth 1. Rivers contain absolutely no salt or minerals at all. False, as we covered. Rivers do carry dissolved minerals, just at a much lower concentration. Myth 2. The ocean is constantly getting saltier every single year, with no end in sight. Not accurate on a geological timescale. Salt removal processes keep the overall level roughly balanced. Myth 3. All oceans and seas around the world have exactly the same salt concentration. Also false. Local evaporation and freshwater input create real, measurable regional differences. Myth 4. Freshwater lakes never contain any salt whatsoever. Not quite true. Most freshwater lakes have some dissolved minerals too, just usually very little. Myth 5. Ocean salt comes almost entirely from ancient sea creatures dissolving over time. Not accurate. The vast majority comes from rock weathering and hydrothermal vents, not from marine life itself. Myth 6. If you boiled all the salt out of ocean water, you'd be left with something close to soap. Not true at all. You'd simply be left with plain, pure water and separated table salt. Let's wrap up with a few fun extra facts. If you somehow evaporated the entire ocean, the leftover salt could reportedly cover all the continents. Estimates suggest that layer would stand roughly as tall as a multi-story building, spread evenly across land. The saltiest natural body of water on Earth isn't the Dead Sea. That title goes to a small Antarctic pond. Don Juan Pond in Antarctica is so salty it rarely freezes, even in extremely cold temperatures. Ocean salt also plays a huge role in driving global ocean currents that help regulate Earth's climate. Salter water is denser and heavier, so it sinks, while less salty water tends to stay higher up. This density difference helps power a massive system of currents scientists call the global conveyor belt. That system moves heat around the entire planet, influencing weather patterns far from the ocean itself. So the same salt that stings your eyes at the beach also quietly helps steer global climate patterns. Okay, let's bring this all together. Rivers do carry salt, dissolved from weathered rock, but they're just passageways, not final destinations. The ocean is where water evaporates, leaving salt behind, while fresh rain feeds rivers with brand new minerals. Hydrothermal vents add even more salt directly from the ocean floor, completely separate from rivers. Terminal lakes like the Dead Sea prove the whole mechanism, trapping salt with no outlet to escape through. And despite constant salt input, natural removal processes have kept ocean salinity roughly stable for ages. All from one simple taste test almost everyone has done, but never actually questioned the reason behind. If this answered a question you never knew you had, that's exactly what this channel is about. So if you enjoyed this, hit subscribe so you don't miss the next one. It genuinely helps this channel grow, and it takes about 2 seconds. Drop a comment and tell me which part surprised you the most. Was it the hydrothermal vents? The Earth age miscalculation? Let me know. And if you like this video, go ahead and tap that like button. It's a small click that genuinely helps this channel keep growing. There are hundreds of everyday questions just like this one waiting to be explored. Things you've tasted or seen your whole life, but never actually questioned. That's what this channel is all about. Toggling your curiosity on, one question at a time. One more thing before you go. Tap that notification bell too, so you actually see it when the next video drops. Next time, we're tackling why flamingos stand on one leg for hours without falling over. It's a surprisingly clever energy-saving trick, and you will not guess the mechanism. I'll see you in the next one.